Good day, students. Today let us look into Fresnel diffraction due to a narrow slit. Now, when light passes through a narrow slit, the emerging wavefront will have the shape of a cylindrical wavefront. Okay, so that has to be taken into account. Here we have the yellow wavefront representing the cylindrical wavefront emerging from a narrow slit. The cylindrical wavefronts emerge from the narrow slit, and hence the wavefront is divided into half-period strips to consider Fresnel diffraction. Now we draw the straight line from the source S here through the wavefront towards the screen, and the distance from the source to the wavefront is small a. Distance from the wavefront to the screen at point P is small b. Now from the point P, we draw lines of path differences lambda by 2 towards the wavefront. So the first line will be b plus lambda by 2, and it will touch the wavefront at this position. Now if we draw a line across this wavefront at this point, we will get a strip, and this is called a half-period strip. Similar lines are drawn at paths b plus 2 lambda by 2, b plus 3 lambda by 2, b plus 4 lambda by 2, etc. up to b plus n lambda by 2. Okay, so the path difference towards successive half-period strips is lambda by 2, and these strips are called half-period because they have an average period of pi by 2. Here, if we closely observe, we see that from the central point of the wavefront, we have the first half-period strip above the center, second half-period strip, third half-period strip, fourth, etc. So we have n number of half-period strips above the central point. Likewise, we have similar number of half-period strips below the center also. Okay, now let us try to calculate the width of a single half-period strip. For that, let us take into account this shape of the wavefront. So we have a central line SOP passing through the center of the wavefront, and we have different points M1, M2, M3, etc. that make paths of b plus lambda by 2, b plus 2 lambda by 2, and b plus 3 lambda by 2 towards the point P on the screen. AB, the radius of the cylindrical wavefront. So considering the triangle SM3P and using the cosine law there, we can write PM3 square is equal to SM3 square plus SP square minus 2 SM3 SP cos theta 3, where theta 3 is the angle between SM3 and SP. Now writing in this in terms of A, B and B plus lambda by 2 path differences, I can write PM3 is B plus 3 lambda by 2. So the square is equal to A square plus A plus B whole square minus 2 times A into A plus B cos theta 3. So we have the expression B plus 3 lambda by 2 the whole square is equal to A square plus A plus B whole square minus 2A into A plus B into the expansion for cos theta 3, 1 minus theta 3 square by 2. The other terms of theta raised to 4, theta raised to 6 are neglected. Now to generalize, we take for Pmn square, we have the relation B plus n lambda by 2 the whole square is equal to A square plus A plus B whole square minus 2A into A plus B into 1 minus theta n square by 2. Now expanding this expression on both sides, we get this term B square plus Bn lambda plus n square lambda square by 4 is equal to A square plus B square plus 2AB minus 2A square minus 2AB plus A square theta n square plus AB theta n square. Here, the a square terms cancel out and b square terms also cancel out. Then n square lambda by 4 is neglected as it tends to 0. It is a very small value. Thus, the remaining terms can be written as bn lambda is equal to a square theta n square plus ab theta n square. That is equal to a into a plus b theta n square. Hence, we can write theta n is equal to square root of b lambda divided by a plus b into a into square root of n. That is, theta n is equal to a constant k into square root of n. Now, theta n is the angle towards each half period strip from the source. Now, the arc OMN can be written as product of radius and angle, that is a into k times square root of n. Hence, the width of the first half period strip is obtained as AK. Square root of 1 is 1, so AK. Now, the width of the second half period strip is, we will be calculating OM2 minus OM1. Okay, so we get the width of the second half period strip as AK root 2 minus AK, that is AK into root 2 minus 1. Now, the width of the third half period strip will be likewise AK into root 3 minus root 2. So, from this we infer that as the order of the strip increases, its width decreases, and as the order of the strip increases, its area will decrease. Now, let us calculate the intensity of light on the screen. Now, the amplitude at P due to the strips above the center of the wavefront O is contributed by the half period strips from above that center point. That is, we have amplitude from first half period strip R1, then amplitude from second half period strip R2, but since its phase is changed by pi by 2, it will be minus R2, then plus R3, minus R4, etc., plus or minus Rn. Now, if we rewrite this expression by substituting R1 for R1 by 2 plus R1 by 2, then R2 as average of R1, R3, we can do simplification and we get this to be approximately equal to R1 by 2. Now, likewise, we get the amplitude of light from below the point O also. Hence, amplitude due to strips below O is given as R1 minus R2 plus etc. plus or minus Rn, again approximately equating to R1 by 2. Hence, the total intensity at P, the total amplitude at P will be R1 by 2 plus R1 by 2, that is equal to R1. Thus, intensity I is proportional to R1 square for Fresnel diffraction due to a narrow slit. Let us consider the Fresnel diffraction of a cylindrical wavefront at a knife edge. So, what happens when a cylindrical wavefront meets a straight edge or narrow edge? This wavefront, it happens to meet a sharp edge, okay, and light will diffract across this edge and form a pattern on the screen. Let's study its behavior. Now let's draw a straight line from the source towards the screen, making contact with the knife edge. So the point of contact at the knife edge is assigned as O, and the center of the screen is assigned as C. Now let us consider a point P above C. Here, if we draw a straight line from the source towards the point P, it will cross the wavefront at O prime. And if we consider another point below C, and draw a straight line from the source towards the screen, it will meet the wavefront at O double prime. Now let us try to calculate the amplitude of light reaching the point P. If this region OO prime contains only one half period strip, the point P will get light from the single half period strip below O prime and all other strips above O prime. So the amplitude of light below O prime will be only R1 and the amplitude of light above O prime will be R1 by 2. Adding it, we get 3R1 by 2. Hence, the intensity of light at P will be proportional to 9R1 square by 4. That is considerably a bright region. Now, if we take the next assumption that this region O prime contains two half-period strips, the amplitude at P will be due to amplitude of the two half-period strips below O prime and amplitude of all the half-period strips above O prime. Okay. So the amplitude of light above O prime is given by R1 by 2 plus the amplitude of the first half period strip below O prime R1 and amplitude of second half period strip below O prime minus R2. Now this sum will be greater than R1 by 2, right? It will be just greater than R1 by 2. And the intensity at that point is considerably proportional to R1 square by 4 and comparatively and comparing it with the earlier value, this region will be a darker region. Okay, so we come to the conclusion that if OO prime contains odd number of half period strips, the resultant intensity is bright but with decreasing intensity. Whereas if OO prime contains even number of half period strips, the resulting intensity is dark. Now at points below C here, light is contributed only by the half period strips coming from above O. All the half period strips below O are blocked by the knife edge and only the half period strips from above O contribute to this region. Now let us calculate the positions of maxima and minimum intensity above C. Now to calculate whether the point P is a region of maxima or minima, we have to find the path difference between the rays that are diffracted towards that point. So taking the path difference delta, OP minus O prime P, we can write this is equal to OP is equal to B square plus Xn square the whole raised to 1 by 2. Okay. Minus O prime P can be written as A plus B whole square plus Xn square the whole raised to half minus A, right? Minus A. Now expanding this equation, we write B is taken outside, so we get B into 1 plus Xn square by B square whole raised to 1 by 2 minus, then A plus B is taken outside into 1 plus Xn square by A plus B whole square in raised to 1 by 2 plus A. So this expression becomes B plus Xn square by 2B minus A minus B minus Xn square by 2 A plus B plus A. That is Xn square by 2 into 1 by B minus 1 by A plus B. That is equal to Xn square by 2 into A divided by B into A plus B. Now, if P is a point of maximum, the path difference should be an odd integral multiple of half wavelength in diffraction. Okay, so here the path difference Xn square by 2 into A by B, A plus B is equated to odd integral multiple of lambda by 2. From that I can write Xn is equal to square root of 2n plus 1 into A plus B, B lambda divided by A. So at this point you get positions of maxima. Likewise, for the point P to be a minima, the path difference should be n lambda. That is Xn square by 2 into A by B, A plus B is equal to n lambda. This gives Xn is equal to square root of 2n into A plus B, B lambda by A. So at this position for Xn we get minima. Now let us try to draw the intensity distribution obtained from this. This is the pattern that we obtained. So above C, we get a diffraction pattern of alternate bright and dark regions. The intensity of the bright points is continuously decreasing, and the intensity of the minimas is continuously increasing. Finally, we will get uniform illumination. At points below C, the intensity of light is gradually decreasing towards darkness. So hence we can write, in the exposed region above C, a diffraction pattern is observed with intensity of bright fringes decreasing and that of dark fringes increasing as we move away from the center. Finally, we get uniform illumination. In the geometrical shadow region below C, the light intensity gradually decreases as we move away from the center. In today's session, we studied about the Fresnel diffraction from a narrow slit. We studied about the nature of the wavefront, the area of the half-period strips in the wavefront, and the intensity pattern when light is incident on a knife edge. That's all for today. Thank you.